So today we are going to start our new chapter, that is, you can say, uh, oscillation in the spring. Okay, oscillation in case of a spring. Okay, so what will happen, I will give you a simple example. Suppose this is the rigid surface. Okay, and here a spring is being attached like this. Okay, and here you can see that another movable object is being attached to the spring. Okay, so now what I will do, I can do either compression or expansion, right? So let me take the expansion case. So if I will expand this box up to a distance x by applying some force, okay, and when I will leave from this position, okay, this to this displacement is obviously x. Okay, so when I will leave this product, leave this object at this particular point, what will happen? It will tries to come back to its original position. Okay, it will try to come back to its original position by applying which force? By applying a restoring force. Okay, obviously everybody in the world wants to stay at their original position. They doesn't need any change. So if any change occurs, they always try to come back from that one, right? So what they will apply? They will apply a opposing force, that is known as the restoring force. Okay, and that restoring force will be in opposite direction. So where you are displacing, you are expanding it in this direction with a displacement x, and there is a opposing force in this direction, or restoring force in this direction. So force and displacement are opposite in direction, right? So if I can write the equation, then force, okay, of restoring is directly proportional to your displacement, because how much you will displace, okay, that much amount of force is going to be produced, right? So this force is obviously depending on your x. What kind of force is this? Force is your opposing force, or you can say restoring force. So F equal to x. So if I will remove this proportionality symbol, this will become F equal to kx. Okay, one constant will be multiplied and it will be F equal to kx. But here, as you can see, the displacement and the restoring force, as they both are opposite in sign, okay, opposite in direction, so that's why I will apply a negative sign here. So F equal to minus kx. Okay, so the formula is F equal to minus kx. Let me write it again. The formula is F equal to minus kx. My main intention here to find out the time period of oscillation in the spring, right? So here this force, I can write it as ma, because mass is there, and with acceleration it will come back to its original position, will try to come back to its original position. Ma is equal to, in the next step, let us take the magnitude value. Okay, so that means I am avoiding the negative sign. So ma equal to kx, right? So here I will just find out what is displacement upon acceleration. Displacement is x, acceleration is a, so this will be x upon a. This a will go here, x upon a, then this k will be going here, m by k. Okay, so x upon a is equal to m divided by k. X by a equal to m by k. Okay, this one I found out. Why, in your mind, that why I found x by a equal to m by k? Because the general formula for the time period is what? 2 pi. Okay, root over of displacement upon acceleration, right? So if I don't know what is displacement upon acceleration, then how can I will put, right? So displacement upon acceleration is nothing but x by a, and just now I found what? X by a's value, m by k for the spring case. So just place this m by k here, right? So let us place it, okay, and write it down in the clear form. This will be 2 pi into root over of x upon a. This will be 2 pi into root over of m by k. This is the formula for the time period in the spring. Okay, T equal to 2 pi into root over of m by k. Okay, so now types of oscillation. Okay, how many types of oscillation are there? One is forced oscillation, and another one is free oscillation. Okay, free oscillation is what? if if some boy is oscillating a pendulum, okay, what he will do, will just take this pendulum from mean position to the extreme position, and then he will leave that one. Okay, when he will leave, then a oscillation will take place. That kind of oscillation where the force is withdrawn, what he is doing, he applied the force, and after that he left that one. Okay, he left his hand. Okay, after that what is happened, force is withdrawn. Okay, force is withdrawn. So this kind of thing where the force is withdrawn, this kind of oscillation is known as free oscillation. Okay, next thing is your forced oscillation. Okay, what is your forced oscillation? The forced oscillation is, up to this all of you understood, yes or no? Okay, so next is forced oscillation. Forced oscillation means if that boy is continuously applying a force in order to oscillate it. Okay, he is applying the force, he is taking this one to the extreme end, then again he is applying the means leaving that one. Okay, while coming back to here, when he observes that it is the process is going slow down. Okay, at this point, at this extreme end, again he applies the force. Okay, then what you can say, here he is not leaving the force, or you can say he is continuously applying the force. Okay, from both the extreme ends. Okay, so if the force is not withdrawn, okay, then that is known as forced oscillation. Okay, that kind of oscillation is known as forced oscillation, where he is continuously applying the force in order to make the oscillation as it is, means there should not be any slowdown of oscillation, right? Based on this, there will be two types of oscillation. One is known as your undamped oscillation. Okay, undamped oscillation, undamped, undamped oscillation. Okay, what is the meaning of undamped oscillation? Is a constant oscillation, right? If the force is not withdrawn, the last case that I told, last case, if the force is not withdrawn, then obviously there will be a constant oscillation like this. Okay, constant oscillation like this. Okay, there will be no change in amplitude. Okay, there will be same, that will be same everywhere. Amplitude means the maximum positive and highest negative, highest points. Okay, so what is happening here, a constant oscillation is going to be produced. Okay, so this is known as undamped oscillation. What is the example? Best example is your alternating current. In alternating current, what is happening? In alternating current, constantly the oscillation is taking place, or constantly the force is what you can say, the force is being applied there. Okay, if that is not constant, you can see a voltage current variation in your home, right? That is not happening. So generally AC is having a constant and simultaneous, or you can say constant and perfect oscillation, that you can say undamped oscillation, undisturbed oscillation. Second case is damped oscillation. What is a damped oscillation? A damped oscillation is when the oscillation is slowed down. Okay, when the oscillation is slowed down. Okay, that is the natural process. One boy is taking this pendulum from mean position to the extreme position. After that he will leave, and then the oscillation will take place like this. Okay, first it will move with a faster one, and at last moment it will slow, and at last it will stop. So the oscillation will be somewhere like this, extreme to extreme, then slow like this, and then stop. Okay, so this kind of oscillation is known as damped oscillation. Why it is happening? Because of the opposing force that is being applied. Opposing force is obviously the restoring force, right? And also due to the air particles also, they are applying it depends on where you are oscillating. You are oscillating in vacuum or you are oscillating in the water, right? So water is having, you can say, viscosity. So due to viscosity, the slowdown will become, or you can say velocity will become slow down immediately in that water, right? So if I will draw the diagram for the damped oscillation, obviously the process is slowed down, right? So the graph will be somewhat like this. Okay, first will be, it will be higher, then lower, 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 and that it will stop. Okay, so this is the, what you can say, the graph. You can see here gradually it is decreasing. Okay, gradually the amplitude values are decreasing, and here you can say the formula is force of force of damping. Okay, force of damping is directly proportional to your velocity. Okay, force of damping is directly proportional to your velocity, because whenever your velocity is there in this direction, okay, suppose the velocity is in this direction, okay, or you can say if your velocity is acting in your this direction, so force of damping will be in the opposing direction, because it wants to stop, obviously. Or when your pendulum is going from extreme position, this is the extreme position, to the mean position, the force of damping, this is the velocity here acting in this side, okay, velocity, so force of damping will be in the opposite direction. Okay, and obviously it is depending upon the velocity. Okay, so force of damping is directly proportional to the velocity. Okay, so you can write it as Fd is equal to V. Okay, is equal to one constant B and multiplied with V applied with a negative sign. Why negative sign? Because force and velocity, okay, force and velocity are in opposite direction. Okay, so Fd equal to minus Bv. Okay, force of damping is directly proportional to your velocity.